Imagine the universe, a vast expanse of wonders. Among them, neutron stars shine, not with light but with mystery. These are incredibly dense objects, remnants of massive dead stars. They challenge our understanding of matter, space, and time. Consider something truly extreme, an object unlike any other. Neutron stars fit this description. They are cosmic laboratories naturally. Here, physics operates at its limits. Gravity crushes with immense force. Temperatures and pressures soar. We learn so much from them. What lies deep inside them? This is a profound question. Could it be a new state? A state of matter unknown on Earth, perhaps made of fundamental particles called quarks, roaming free. This idea excites scientists. It pushes the boundaries of knowledge. Our journey begins now, into the heart of these stars. We will explore their formation, their bizarre, unique properties, and the tantalizing possibility that quark matter lurks within. Join me as we delve deep into the neutron star mystery. Stars live and stars die. Our sun is one such star. But some stars are giants, many times more massive. They burn fuel furiously, creating heavier elements inside. Iron, nickel, gold, all forged in these colossal stellar furnaces. When a massive star ages, its core fills with iron. Iron cannot fuel the star. Fusion reactions stop there. Gravity then takes over. The star's own weight crushes it. An unstoppable inward fall begins. The star starts to collapse. This collapse is catastrophic. It happens in mere seconds. The core shrinks dramatically. Outer layers crash down hard. They rebound with immense energy. A titanic explosion occurs. This is a supernova, a brilliant cosmic spectacle. The outer layers blast into space, enriching the cosmos with elements. But what of the core? It continues its collapse. Protons and electrons are forced to merge into neutrons. A tiny dense object forms. A neutron star is born. Let's talk about density. Neutron stars are unbelievably dense. Imagine our entire sun squeezed into a tiny ball. A ball just a few miles wide, the size of a city perhaps. This is a neutron star. Matter packed beyond imagination. A single teaspoon of it, if brought to our Earth, would weigh billions of tons. More than a mountain, easily. This density is staggering. It's hard to truly grasp. Neutrons are packed tightly, like sardines in a cosmic can. These stars are not just dense, they also spin incredibly fast. As the parent star collapsed, it spun faster and faster, like an ice skater pulling in arms. Some spin hundreds of times every single second. They can emit beams of light. These are pulsars. And their magnetic fields? They are astronomically strong. Trillions of times Earth's field, the strongest magnets known. Some are called magnetars. Their fields are even more intense. These properties make neutron stars unique laboratories for physics. We know about atoms, protons, neutrons, and electrons. But are protons and neutrons fundamental? The answer is no, they are not. They are made of smaller pieces. These pieces are called quarks. They are truly elementary particles as far as we currently know. There are 6 types of quarks. Scientists call them flavors: up, down, charm, and strange, and also top and bottom. Protons, for example, are made of 2 up quarks, 1 down. Neutrons have 2 down quarks and 1 single up quark. What holds quarks together? A force called the strong nuclear force. This force is incredibly powerful. It is carried by particles. These particles are called gluons. Think of them as cosmic glue. They bind quarks tightly inside protons and neutrons. This binding leads to a property called confinement. Under normal conditions on Earth, quarks are never found alone. They are always trapped, confined in groups, forming particles like our familiar protons and also our familiar neutrons. Section 5. Beyond confinement, the idea of quark matter. What if conditions are not normal? What if pressure is immense, or temperature is incredibly high? Could quarks then break free from their proton and neutron prisons? This is a key question for physicists exploring matter in its most extreme states. Scientists theorize a new state, a state called quark matter, or sometimes quark-gluon plasma. In this state, quarks roam, and gluons too, freely. They are no longer confined within individual particles. It's a soup of quarks and gluons. Think of water changing states: solid ice, liquid water, gas steam. Quark matter is another state, but far more fundamental. It represents matter dissolved into its most basic constituents, a primordial state of being that existed in the early universe. We can create tiny bits of this quark-gluon plasma in giant particle accelerators, like those at CERN in Europe. For a fleeting moment, it exists. But neutron stars might offer more, a stable, natural environment for dense quark matter to exist. Section 6. The ultimate squeeze quark matter in neutron star hearts. Let us return to neutron stars. Remember their incredible density. Gravity inside them is relentless. It crushes matter with ferocity. Deeper inside the star, the pressure grows even higher, beyond anything we can replicate sustainably here on Earth. What happens to neutrons then, under such enormous pressure? Do they remain as neutrons, or do they break apart? The hypothesis is fascinating. Neutrons might dissolve into their constituent quarks right in the star's core. This would create a quark core, a heart of deconfined quarks. It might contain up quarks and down quarks naturally, but also perhaps strange quarks, forming strange quark matter. This is a truly exotic idea, a new phase of matter. This remains a hypothesis now. We cannot drill into a star. We cannot take a sample. Direct observation is impossible. So scientists must be clever. They use models and observations of the star's external behavior to infer what lies within. Section 7. Cosmic clues searching for evidence of quark cores. How can we find evidence for these hidden quark cores? One way is to measure stars, their masses, and their radii with extreme precision. This is a difficult task, but technology is advancing, giving us new cosmic eyes. The presence of a quark core would change how the star behaves. It affects the equation of state, which links pressure to density. A quark core might be softer, more compressible than neutrons. This would allow stars to be smaller for a given mass. Recent cosmic events help. Gravitational waves from mergers like event GW170817 and X-ray telescopes like NICER. NICER is on the space station. It measures star sizes precisely. These observations provide limits on neutron star properties. Some of the most massive and most compact neutron stars seem to challenge our models based purely on neutrons. Their small sizes might hint at something softer inside, like a core of quark matter. The debate is active and exciting. Section 8. A deeper understanding why quark matter matters. If we confirm quark cores, it would be revolutionary. For particle physics, it's huge. Our theory of strong interactions, called quantum chromodynamics, QCD, would be tested in a new way, at densities found nowhere else, validating our fundamental theories. Astrophysics would also transform. Understanding dense matter is key for modeling supernova explosions and neutron star collisions. These collisions create heavy elements like gold and platinum. Quark matter could change how these events unfold. This could also teach us about the very early universe. Just moments after the Big Bang, the cosmos was a hot soup, a soup of quarks and gluons. Neutron stars are like windows into that primordial state, a cosmic time machine. The discovery might even hint at physics beyond our current grasp. Are there even more exotic forms of quark matter we haven't imagined? Could new forces be at play in these incredibly dense realms? Neutron stars hold the potential for profound new discoveries. Section 9. The quest continues. Future of neutron star research. The biggest challenge remains clear. We cannot directly see inside a neutron star's dense core. It is hidden from our view. We rely on indirect methods, interpreting light and gravity from these distant tiny objects. It's a cosmic detective story. But new tools are coming. Future telescopes will be sharper. X-ray observatories more sensitive. Radio astronomy will improve, tracking pulsars with precision. Next-generation detectors for gravitational waves will reveal more about the mergers of these stars. Theoretical work must also advance. Simulating quark behavior is hard at such extreme densities. The physics is very complex. Supercomputers run massive calculations to model these exotic states. Theory and observation must work hand in hand, step by step. So, our cosmic quest continues to unveil the quark matter mystery locked inside neutron stars. It's a journey to the heart of matter, of gravity, of existence. The universe still guards its secrets, but with curiosity and science, we continue to explore. Always.